Hello students, this is Professor Chalai, and in this video we're going to talk about the laws of multiple proportion and the law of definite proportion. And as always, you can follow along in our Chapter 2 workbook. But before I do so, let's first briefly talk about Dalton's atomic theory, which was established in 1808 by somebody called Dalton, I suspect. Um, and this is just an example of how the scientific method changes our idea of what's the established theory over time. Because Dalton, back in 1808, uh, Dalton's atomic theory states that each element is composed of tiny indestructible particles called atoms. Now, we know that that is somewhat true, but also not quite true, because today we know that atoms can be destroyed or can be separated into protons, neutrons, and electrons. So they're not really indestructible. And even then, protons and neutrons can be separated into quarks, which we're not really going to talk about in chemistry. So the very first sort of statement of Dalton's atomic theory we have found to not quite be true since in the 200 years since. His second statement in his atomic theory states that all atoms of a given element have the same mass and chemical properties. Now, the second part of this is true. Today, we know that all atoms of the same element have the same chemical properties, but they don't have the same mass. And we'll learn about this in the next video when we talk about isotopes. His third statement states that atoms of different elements have different properties. This is true. Atoms combine in simple whole number ratios to form compounds. This is also true. We don't have compounds with half of an atom. And lastly, it states that atoms of one element cannot change into atoms of another element. In a chemical reactions, atoms only change the way they're bound together with other atoms. This is sort of true. In chemical reactions, for the most part, atoms don't change type. They only change how they're bound together. But we also know that atoms can change from one element into another through radioactive decay, for example, or fusion in the sun, where hydrogen atoms are fused together to form helium atoms. So, but for the most part, we can consider that atoms are fixed in chemical reactions. They only break bonds and form bonds. Atoms changing from one element into another, we'll leave that for the physicists to handle. So that's just a brief overview of Dalton's atomic theory and how different or not our understanding is, how much or not our understanding has changed over the past 200 years. Okay, let's look at the laws of definite proportions and multiple proportions, because these are some of the early ideas about how molecules and atoms interact with each other. And so the law of definite proportions states that all samples of a pure substance let's call it compound, of a pure compound, contain the same element in the same proportion by mass. Now, this is back when we sort of had an idea that atoms exist, but we couldn't exactly separate them and count them the same way, using the same sort of precision that we can today. But we could have measured the mass. So, for example, if you have two samples of pure water, today we know that water is made up of, the molecule for water is H2O. But back then, all that we may have known was that water is made up of hydrogen and oxygen. And so what this statement is saying is that if you take two samples of water and you measure the mass of hydrogen that you have in one, and measure the mass of oxygen you have in one and compare that to the same ratio in the other, you should get the same ratio. So for example, in one sample, if you measure 1 gram of hydrogen and 8 grams of oxygen, and in the second you measured, let's say, 2 grams of hydrogen and 16 grams of oxygen, those are actually the same ratio. If we simplify this by dividing by 2, we get that those ratios are the same, 1 gram to 8 gram. And that's the law of definite proportion. It says that it doesn't matter where you get the sample from, the ratios of their elements are going to always be the same, the ratio by mass. This is sort of a precursor to what we understand now by all molecules having the same formula, regardless of where you get them from. Water is going to be H2O, no matter where you get it from. Water in a cup versus water in the ocean, it's going to be H2O. Okay, so that's the law of definite proportion. Just to highlight, this deals with the same compound. The same compound should have the same ratios of their masses of elements. The law of definite multiple proportion, states that two elements react when two elements react, to form more than one compound. There we go. To form more than one compound, a fixed mass of one element will react with masses of the other element in a ratio of small whole numbers. Now, what does this even mean? Well, let's come back to our example of water. Let's say hydrogen reacts with oxygen to give us water, but hydrogen can also react with oxygen to give us hydrogen peroxide. Back then, again, we may not know the formula of chemical compounds, but if we had two samples where we had maybe 1 gram of hydrogen reacting with, again, 8 grams of oxygen to form compound, let's call it A, and in another situation we have 1 gram of hydrogen reacting with, let's say, 16 grams of oxygen to form compound B, these ratios, let's express those ratios. So this ratio is 8 to 1, so 8 over 1 divided by this ratio, 16 over 1, is actually 1 over 2, right? 8 over 16 is 1 over 2. These are small whole number ratios. Small whole number ratios. And what that's saying is that when you have the same two elements, hydrogen and oxygen, let's use a different color, hydrogen and oxygen in both cases, reacting to form two different compounds, if you take the ratios of their masses, the first case and the second case, they're going to come out to be a small whole number ratio. And this is the law of multiple proportions. It deals with different compounds, there we go, but the same elements. Now, if the ratio was 1 over 1, then it's just a law of definite proportion because it's the same compound, and that means A was equal to B. But because these two numbers are different, they're two different compounds. Now, all this is saying, really what this is saying is that when the elements combine together, they really don't combine in fractional amounts. Like we have H2O and H2O2, but we really don't have a compound like H2O 1.5, for example. There is no half of an atom in a compound. That's really what the law of multiple proportion says, just in a very roundabout manner. So let's see these in practice. So question 1 says we have two compounds, A and B. We don't know whether they're the same or different. But compound A gives us 1.39 grams of hydrogen and 22.24 grams of oxygen, whereas compound B gives us 0.42 grams of hydrogen and 13.44 grams of oxygen. Do these compounds follow the law of multiple proportions? Well, let's figure out. So compound A, we have 1.39 grams of hydrogen to 22.24 grams of oxygen. Let's make this a simple ratio of 1 to something. So let's divide by 1.39. So this will give us 1. Divide by 1.39. So this will give us 16. There we go. So this actually simplifies to 1 gram of hydrogen for 16 grams of oxygen. Compound B, on the other hand, is 0.42 grams of hydrogen to 13.44 grams of oxygen. Again, let's simplify this. So this is 1. And that will give us 1 gram of hydrogen to 32 grams of oxygen. So let's look at the whole number ratios, because it's a law of multiple proportions. 16 to 1, so 16 over 32, whoops, not 13, which is 1 over 2. Again, simple whole number ratio, so yes. They follow the law of multiple proportions because we just showed that using the math. So what this means is, yes, they follow the law of multiple proportions, and really everything should follow the law of multiple proportions because, again, atoms can't form compounds with fractional ratios. The fact that it's a ratio that's not 1 over 1 means that it's not a law of follow the law of definite proportions. So do these compounds follow the law of definite proportions? We can say no, because of the same calculations above. Their ratios are different in exactly 16 to 1 and 32 to 1. Those are the ratios. So what does this mean? Are compounds A and B the same? Why or why not? Well, the answer is no, they're not the same, because while they follow the law of multiple proportions, everything should, they do not follow the law of definite proportions. And remember, the law of definite proportions deals with the same compound. So if they do not follow the law of definite proportion, then they are not the same compound. I hope that makes it clear. Let's do a quick second example. So 2 samples of sodium chloride are decomposed. Pause the video here. Try to work it out on your own first, and then you can unpause and I'll go over the answer. Okay, so we have 2 samples of sodium chloride. One produces 6.98 grams of sodium and 10.7 grams of chlorine. We'll call that sample A. And another produces 11.2 grams of sodium and 17.3 grams of chlorine. We'll call this sample B. So let's look at their ratios one sample at a time and simplify them first. So for sample A, we have 6.98 grams of sodium, Na is sodium, to 10.7 grams of chlorine, Cl, which simplifies to, if we divide by 6.98 on both sides, we get 1 gram of sodium to about 1.53 grams of chlorine. For sample B, we have 11.2 grams of sodium to 17.38 grams of chlorine. Again, simplify by dividing both sides by 11.2. We get 1 gram of sodium to 1.55 grams of chlorine. Okay, so now let's look at these ratios, because they're asking us whether they're consistent with the law of definite proportion, meaning they should have the same ratio of masses. 1 to 1.53 versus 1 to 1.55. I would say to this question, yes. They follow the law of definite proportion. Now, you might be asking or saying to yourself, well, 1.53 versus 1.55, they're not quite the same number. But I just want to point out something that we looked at earlier. Remember that I said that if we have 2 markings, let's say 1 and 2, and we took a measurement, let's say the measurement was here, that was somewhere in between, let's call it 1.4 instead of somewhere in between these 2 values, we made a guess for this very last digit. And so oftentimes, if 2 numbers are off by in the very last digit, the last significant digit that you have, and you're comparing them and they're off by a little bit, then that's okay. You can say that they are sort of roughly equal to each other, or equal to each other even. Because usually in measurements, we make a guess for that last digit. So this is okay to compare numbers like that. Okay, that brings us to the end of the laws of definite and multiple proportions. They've been used for, certainly over 100 years to understand elements and compounds and how they're made up. And really, they're precursors to really saying two things. One, elements, compounds of the same type, regardless of where you get them from, will have the same composition. Water is H2O regardless of where you get it from. That's definite proportions. And the second one, law of multiple proportions, which is really just a fancy old-timey way of saying atoms bind in whole number ratios. You don't have half an atom or a quarter of an atom binding. That will bring us to the end of this video. In the next video, we're going to look at the atomic structure. I'll see you then. Bye.